Hi everyone. Many motion control applications are driven by a DC motor, and that DC motor is in turn driven by an amplifier, and that amplifier is in many cases an H-bridge, where the transistors or MOSFETs are included in an H configuration, what we see over here. My name is Stef Intraak, and in this video we are going to talk about the different H-bridge topologies, or in other words, the different ways in which that H-bridge can function. In this video I will not go into the operation of the different components, and I will limit myself to a voltage controlled amplifier. So first of all, let's look to a more or less standard applications, in which we have a PMDC motor over here, which is driven by an amplifier. And an amplifier is connected to a CPU through some I/O. And most of the time in a position control application we have an encoder connected to the motor which communicates to that CPU by some I/O over here. And of course there is a load connected to the motor, and in for instance a printer application we have a belt transmission over here which drives some pinches over here which moves paper within the forward and backwards direction. So what we see is that we have an operation in which the speed of the motor should be either positive or negative, but we also need positive and negative torque because, for instance, we have to accelerate and decelerate. Well, knowing that, we can draw a so-called four-quadrant matrix in which we put the speed on the horizontal axis and the torque on the vertical axis. And we have, as we have seen, requirements for a positive speed and a negative speed, and we have requirements for a positive torque and a negative torque. So that is what we call by a four-quadrant operation. So we require from that amplifier that it has to be able to operate in a 4Q and a 4-quadrant operation. And therefore we most of the times use an H-bridge. And we have four basic topologies for H-bridge amplifiers. The first one is so-called unipolar control. The second one is quasi-unipolar control or sign magnitude control. The third one is bipolar control, also known as locked antiphase control. And the last one is quasi-bipolar control. So first of all, let's talk about unipolar control. This is my H-bridge, and in that H-bridge I have drawn instead of MOSFETs, switches over here, because we use these MOSFETs as switches, so that is quite easy to replace them by switches Q1, Q2, Q3 and Q4. And as you know, within these MOSFETs we have anti-parallel connected diodes, the D1 through D4, and we are going to see that we need these diodes for operation of these different H-bridge types. So what I'm going to do now is look at the behavior of this H-bridge, and we are going to look to the voltages and the current flows. In this situation I have put a positive voltage to MOSFET Q1, so MOSFET Q1 is conducting all of the time. So we can say switch Q1 is closed during the whole operation. So in that case, this is a connection from the power supply VS towards the motor over here. And we put a PWM voltage to MOSFET Q4. So MOSFET Q4 is switching. So when the value of the PWM is positive, then Q4 is closed, and in that situation the current will flow from the power supply through MOSFET Q1, through the motor over here, through the closed MOSFET Q4 to the ground and back to the power supply over here. So the current flow again will be the red one, which is depicted over here. Now let's have a look what happens if Q4 is opened. Then we have to keep in mind that the motor is a series connection of a back EMF, a resistor and an inductor. And when current flows through an inductor, we cannot interrupt the current because that current wants to keep on flowing. And because of that, when opening Q4, the green path is my new current path, because the current will keep on flowing through the motor. So it's a green arrow over here. So my current path is from my power supply over here through Q4, through the motor, and then through diode D2 back to Q1 over here. So this is my current path over here. And here we see why D2 is necessary. Unfortunately, these diodes are always in the MOSFET packages. So now let's have a look to the different voltage and currents. And I also have drawn over here another method, which I have called method B, which is more or less the same method, same situation as method A, only I have replaced the PWM to Q1, and not Q1 is closed all the time, but in this case it's Q4. So looking to the PWM, the voltages and the currents, we get this picture over here. So keep in mind the black curves are related to method 1, and the red curves over here are related to method B, and I'm only going to discuss method A. So please look to the black curves over here. This is my PWM signal, which is connected to Q4 over here. And what we see that when the PWM value is positive, then the voltage VB is equal to the voltage over here, which is 0 volt over here. So when the PWM value is positive, we see that VB is 0. On the other hand, VA is all of the time, VA is equal to the power supply voltage over here, because Q1 is into conduction all of the time. So Q1 is closed during the whole operation. So VA is during the whole operation equal to the power supply, and that is what we see over here. So now when we subtract VB from VA, so VA minus VB, then we get this signal over here. So when the PWM value is positive, also VA minus VB is positive. Now let's have a look what happens when we open Q4. Then the current wants to flow through the motor into the same direction. We see that all of the times VA was positive, which was this line, but now we see that due to the fact that this is my current path, and in an ideal situation in which we use ideal diodes, so the VAK of the diode is equal to 0, we see that voltage VB is equal to the power supply voltage over here, because the current is flowing over here. So we have more or less a connection between the power supply and VB. So in the negative part, or in the 0 part I should say, of my PWM, VB is also equal to the power supply voltage. So VA minus VB is in that situation 0. So now we see that we have a direct relationship between the shape of the PWM and the voltage VA minus VB. When it's positive, VA minus VB is positive, and when the PWM is 0, also VA minus VB is 0. But there is one situation in which this is not the same situation, so to say. What we see when the PWM voltage is positive, we see that the current increases, and of course when the PWM voltage is 0, we see that the current decreases. But when the PWM period time, so the high period time, is very small, we see that that increase in current is small, and in that case it might be possible that in the 0 part of my PWM my current becomes 0 at a certain point. And when that is the case, then there is no more current flowing through diode D2, so there is no connection anymore between VS and that VB point over here, and that means that the voltage we measure across VA and VB is equal to the back EMF voltage. So at that point, so when the current becomes 0, we have the back EMF voltage across the terminals VA minus VB. So for small values of PWM, there is no direct relationship anymore between the PWM signal and the VA minus VB signal, so the voltage across the motor. So in this situation, that relationship is not anymore there, so we call that a non-linear operation of the unipolar control topology. So looking to some properties of the unipolar control, we can see that we have less switching losses because we have only added the PWM to MOSFET Q4, and we do not have a high current ripple because this is a rather this path leads to the situation that the current decrease is not that high, so it has not that negative effect on RFI or EMI. But on the other hand, the main unipolar disadvantages is the nonlinear behavior when the current drops to zero. And certainly in a situation when we want to reverse the current in a forward voltage switching mode, we will notice that nonlinear behavior of that unipolar control switching algorithm. So this is a non-linear amplifier which is not often used in a motion control application where the position occurrences may be high. And on the other hand, we have also the disadvantage of higher conduction losses because we use the diode over here instead of a low ohmic MOSFET over here. So that unipolar control is more or less obsolete. We don't see it that much, especially because of that non-linear operation. Well, then let's look to the so-called quasi-unipolar control, which is also called sign magnitude control, and in the stepper world, the world of the stepper drivers, they often call it slow decay control. What we do in this situation? Well, we put during the whole operation Q1 into conduction, so we close Q1 all of the times, and we put again the PWM to Q4 over here. But the main difference with the unipolar control is that we put the inverse PWM to Q2. And then let's see what happens. So when my PWM value is positive, then Q4 is closed, and then this is again my current path. So the current flows through Q1, through my motor, through Q4 to the ground. When my PWM value is negative, then the inverse PWM is positive. So in that case, Q2 is closed. So my current flows through Q1, through the motor, through MOSFET Q2, back to this MOSFET Q1 again. So this is one of the methods you could use. The other one is method 2, in which we close Q4 all of the times. We place the PWM signal to Q1 and the inverse PWM to Q3. But let us discuss method A and let's see what happens to the voltages and currents again. So also again, please look to the black curves over here because the red ones are applicable for method B. So this is the PWM signal again, and again let's start over here. For instance, when the PWM value is positive, we have seen that the red arrow depicts the current flow through Q1, the motor, and Q4. So we see at that point, we see that VA is connected to the positive voltage over here, so VA is positive. But Q1 is closed all of the time, so VA is positive during the whole situation. When we look to the positive value of the PWM cycle, we also see that Q4 is closed. So in that case, VB is equal to 0. So at the positive value of the PWM, we see that VB equals 0. So VA minus VB is equal to that positive value over here minus the 0 over here, which is a positive value. When Q4, when the PWM cycle is when PWM is 0, then the inverse PWM is high. So the voltage towards Q4 is negative, so Q4 is opened, but Q4 is in that case is closed. So we see that the value of VB equals the power supply voltage because this switch is closed. So VB equals the power supply voltage Vs in that case. So in the negative, or in the inactive, I should say, inactive period of the PWM signal, we see that VB has a positive value. So VA minus VB is 0 in that case. So we see that in that case, the shape of the PWM and the output signal, the voltage across the motor, have the same shape. We also see that during the high value of the PWM, the current increases, and when the PWM is low, we see that the current decreases over here. Now let's look to the situation in which we had very small values of my PWM signal. So Q4 is closed for a short time and Q2 is closed for a longer time. What we see is that during the positive value of my PWM, my current increases, and during the zero part of my PWM, the current decreases again, and in this situation, the current can drop to 0. But because Q2 is closed all of the time during this 0 period of my PWM, because this was my inverse PWM signal, we see that VB is all of the time, when this PWM cycle is 0, that VB is during that time is equal to the power supply Vs again. So also in this period we see that VB has a positive value, so VA minus VB is 0 all of the time. So we don't have that back EMF anymore, what we saw in the unipolar control situation, which means that this kind of operation is really linear. So quasi-unipolar control has a big advantage compared to the unipolar control, that is linear and is complete operation during complete operation from small PWM values up to high PWM values. So looking to the main properties of this switching topology, we can say that comparing to unipolar switching, the positive aspects to the advantage of quasi-unipolar control is that we have lower conduction losses because the ohmic resistance of a MOSFET is much lower than the ohmic resistance of a diode. But the main advantage is that we have a much better linearity when operating in one direction. So we always have, for all the values of PWM, we have a linear relationship between the PWM signal and the output signal VA minus VB. The main disadvantages of the quasi-unipolar switching method is that it's a more complex switching algorithm, because the timing of switching Q2 and Q4 is very important. It's crucial because when for some time, for instance Q4 and Q2 would conduct at the same moment, then we have a low ohmic path over here, which we call cross conduction, and in that case we have a short circuit of the power supply through these two MOSFETs over here, which will destroy that H-bridge. So we have to make sure that we have to so-called break before make contact of these two MOSFETs. So before we put Q2 into conduction, we have to make sure that Q4 is not conducting anymore. And in that very small period, the current will flow through that diode D2 again. So break before make is really necessary, and most drivers take care of that break before make functionality either by setting the break before make dead time by means of an external resistance, or by measuring the fact if Q4 is conducting anymore, and when it's not conducting anymore, then just putting Q2 into conduction. All right, then we are looking to the third topology, which is the bipolar control. And in a bipolar control situation, we put PWM to all four MOSFETs. Other names for bipolar control are the locked antiphase control, and in the stepper world we also call it fast decay control, and we see in a moment why that is the case. As I said, we put PWM to all of the MOSFETs. We put the positive value of the positive PWM signal to Q1 and Q4, and the inverted PWM signal to Q2 and Q3. So now let's look what happens when we have the positive part of the PWM cycle. And in that case, Q1 is closed and Q4 is closed. So the current flows through Q1 through the motor, through Q4 to the ground. When we have the negative part of the PWM signal, then the inverse PWM signal, which is put to Q2 and to Q3, has its positive value over here. So in that situation, Q2 is closed and Q3 is closed. But we have seen that the current flow is was in that direction due to the red arrow over here. So due to the inductance of the motor, the current will keep on flowing into that direction. So in that case, the current path is going from the ground through Q3, through the motor, through Q2, back to the power supply. So that is the case when we have the negative part or the zero part of the PWM cycle. So it's flowing from ground through Q3, through the motor, through Q2, back to the power supply. And due to that current path, the current decrease will be faster, and that is why we call it the fast decay control for our stepper motors. So now again, let's look to the voltage and the current shapes. And again, we have put the PWM signal over here. So when the PWM is positive, we see that Q1 is closed and Q4 is closed. So at these times, VA is positive through the connection over here, and VB is negative through the connection over here. So VA is positive, VB is negative, so VA minus VB has a positive value. When we have the zero part of the PWM signal, we see that the inverted PWM signal, the green signal over here, has a positive value. So then VB is connected through Q2 to the power supply, and VA is connected through Q3 to ground over here. So VA is 0, which you can see over here, and VB has a positive value, which we can see over here. So in that case, VA minus VB equals a negative voltage across the motor, which is almost equal to minus the power supply voltage VS. So that happens for all the PWM values between a very small PWM voltage somewhat higher than 0 up to 100% PWM voltage. What we also see is, for instance, in this situation in which the duty cycle PWM is almost 50%, because the high time and the low time are more or less equal. And in that situation, we see that the currents increase and the current decrease is almost equal, and we see that the average voltage across the motor is 0. So at 50% PWM, we have a 0 average voltage across the motor, which also means that when we have 0 PWM, that we have in that case an almost the negative voltage across the motor. So that could be a potential safety issue, because when, for instance, connection between PWM from your CPU or your I/O board towards the amplifier is lost, then the PWM value is 0, but in that case there is a maximum voltage across the motor, and in that situation, unpredicted things can happen, so be aware of that. So look into all the properties of the bipolar control. We see that the main advantages are the following: that first of all, we have an excellent linearity in the whole operating area, so there is no deadband around 0, which is very good for high dynamic switching operation topologies. We also have a wide bandwidth because the current changes are very fast, and we don't need a signal direction, because by putting the inverted PWM to the opposite MOSFETs, we can only use the PWM signal for changing the average voltage across the motor, but also changing the direction of the motor when we are lower or higher than 50% PWM. The main disadvantages are that we have higher switching losses. So when you have a poor MOSFET or you have a high switching frequency, well, the switching losses will increase. And of course the timing of Q2 and Q4 is very crucial, but also for Q1 and Q3. So also in this case, be aware that you have to make break before make control of these MOSFETs and these MOSFETs, so to avoid cross conduction and to avoid, of course, the short circuit and destroying your MOSFETs in your amplifier. Because the current drops at a faster slope, we could have more RFI or EMI problems. You should look into that. And as I told before, at 0 PWM, the voltage across the motor has a maximum value, and that could lead to potential safety problems. So also be aware of that. Then we have the last one, which is the so-called quasi-bipolar control. And in the quasi-bipolar control, we only put the PWM to Q1 and Q4, and Q3 and Q2 are opened during the whole operation. So there is no current path through Q2 and Q3. So what happens when the PWM value is positive? Well, then again the current flows through Q1 through the motor, through Q4 to ground, and due to the inductor, the current wants to keep on flowing. So when we open Q1 and Q4 during the inactive period of the PWM, the only current path available is through diode D3 over here, which is a green arrow through the motor, through diode D2 up to the power supply over here. So also in this situation, we see that when we have a positive value of the PWM, well, then VA equals the power supply voltage over here, which we see over here, and we see that during the positive value of the PWM, that the voltage VB is 0, and that is depicted over here. So VA minus VB has a positive value. When the PWM is set to 0, then all MOSFETs are open, and then we see that the current will flow through, according to the green arrow, so through D3, and when D3 is an ideal diode, then VA is connected to the ground, so it's 0. That is depicted over here, and we see that current flows through D2 to the power supply over here, and when D2 also is an ideal diode, then VB is equal to the maximum power supply voltage VS over here. So VB has a positive value. So in that case, VA minus VB has a negative voltage, which is the same situation as in the bipolar control operation. The only thing what is different is at the low values of the PWM, because at low values of PWM, there's still the possibility, just like in the unipolar control situation, that current drops to 0, and in that case there is no current flowing anymore through these diodes. So these diodes are not conducting anymore, so VA is floating and VB is VA is floating. So in that case we have a voltage across the motor, which is depending on the back EMF voltage over here. So again, also the quasi-bipolar control has a non-linear operation when the PWM value is low. So that is the main disadvantage of quasi-bipolar control, that it's also a non-linear topology. So the properties of this control topology compared to bipolar switching is that it's of course much easier switching, because we only put the PWM to Q1 and Q4 and not the inverted one to Q2 and Q3, because they are opened for all of the time. So there is also less risk on cross conduction. But compared to bipolar switching, we see that we had a nonlinear behavior, because when the current drops to zero, the voltage across the motor is equal to the back EMF voltage. So we have not that direct relationship anymore between the PWM and the motor voltage, and we could have higher losses because the current flows through diodes and not through MOSFETs over here, and the ohmic resistance of the diodes are in general higher than the ohmic resistance of the MOSFETs. So also this topology is more or less obsolete. Well, comparing all topologies, I've put the main properties over here, and these are the topologies which we discussed. And as I said, the unipolar and the quasi-bipolar topologies are more or less obsolete, so let's not compare them anymore, but look to the quasi-unipolar topology and the bipolar topology. And we see, for instance, that the quasi-unipolar topology has positive aspects on almost every property. So with respect to efficiency, bandwidth, safety, ripple, linearity, etc. Of course, it's somewhat more complex than the obsolete ones, but it's still a very usable topology. On the other hand, we see the bipolar topology, and we see that the linearity is somewhat better and it has somewhat higher bandwidth. But on the other hand, you keep in mind that you might have a safety issue, something which you probably have to look into when using that topology. And on the other hand, you might have somewhat more RFI noise because of the faster switching. So, well, we've seen a couple of H-bridge topologies. We've seen that quasi-unipolar and the bipolar topologies are very much used in modern switching amplifiers. They have good properties, but some different aspects, so please keep that in mind when choosing between the one or the other topology. Well, that's all about the H-bridge and switching of the H-bridge. Thank you for watching, and I hope to see you next time.